All right. So, hi everybody. This is the problem session or live tutorial for uh, the lecture 4 for the category theory crash course. Um, so nobody showed up to the live session, which is totally cool. So I thought maybe you would take some time to go over a problem or two from the last lecture. So I gave you guys two main problems. So one was to show this particular inverse limit or limit in this case is equal to the ring of formal power series in one variable. And then I think one other problem about supremum and how that actually corresponds to a colimit in this case. So let's go through this. So this is the problem we have here. This is a limit. So it took a while for the notation to kind of like crystallize in the mathematical community, but for a while, limits were sometimes called projective limits. Or inverse limits. So inverse meaning this is kind of why the arrow goes backwards pointing versus colimits, sometimes called inductive limits. Or directed limits. So if you see any of these three things for either limits or colimits, this is what they refer to. So this is kind of cool. This is like you can build up these. So these formal power series. Oops, the formal here means, well, this is really, by definition, an infinite sum of things. So if I take some element f of x in here, it is an infinite sum of powers of x with some coefficients. A0 plus a1x plus a2x squared, and so on. It keeps going. Formality here, or formal power series, just means that we consider this as a sum where we don't really worry about any kind of convergence. We just kind of take on faith that the infinite sum is a well-defined thing. And you can make it well-defined. You can think about this thing as an actual ring. This is a ring of formal power series. You can give this thing a topology. You can think about it. Sometimes we'll write like brackets for convergent power series. But we're not really worrying about this right now. This thing also has something called the T-adic topology. And yeah, that is kind of closely related to the idea of p-adic numbers, if you've heard of those from number theory. So what is this saying? That first off, that this thing is an inverse system, or a system that I can take the limit of. And not only that, that this ring over here is equal to this limit. So it has a universal property. So it's satisfied. We have to kind of prove those two things here. So for any m greater than or equal to n, I am going to have a natural morphism. Between these guys. I'll call this psi sub mn So in here, what we're doing is setting some element f of x plus x to the m. That's what the general element of this quotient looks like. Setting that to f of x plus x to the n. Nothing fancy. So you can imagine, if I have this really is a function that doesn't do anything to f. It just kind of includes it into a different um, quotient. This is because if m is greater than or equal to n, then this thing contains this thing. There's more elements here. Okay. So now we claim that oops, our formal power series guy is the sort of universal cone over this family. So we know for every n, we have a natural morphism. Call this guy rho sub n. This is just the quotient. All you're doing is kind of killing off the terms uh, which have degree less than equal to n. Or sorry, greater than equal to n. This takes some power series in blue. And all this map does is kill off all the higher order terms. Okay. So we kind of have to be careful. So what really happens here is this limit is equal to the following. Mhm. It's kind of a subring of the product for all these things. Oops. So this is to denote a subring. Consisting of all like compatible uh, products of polynomials. The subring of the product such that mm, I would say the general element of this thing would be kind of like some indexed family, maybe I'll write like m sub n, such that this is true for any m greater than or equal to n. So we want these to be sort of compatible in a way. Compatible elements. And so we have a unique function into here. And so you can actually show that Um, what we've just shown is the following. And this ring, together with these kind of projection morphisms, are the universal cone over the diagram or over this family. I should say all these morphisms. So universality has to do with the fact that if you have any other cone, so if you have some other ring M mapping to all these other ones, so to each of these for every n, so with some delta n, if there exists this, then there admits a unique map from M into our formal power series ring. So maybe it's big F or something, such that these all commute. Oops. And this just happens because, so if I have a map from M into each one of these quotients, then by definition, I have a map from M into uh, this product right here. And once I have a map from M into the product, being a compatible family maps exactly is this criterion. But I defined this ring of formal power series to be exactly that subring of compatible families. So in reality, it means that M maps into our formal power series ring. It's got a visitor. Hey, right. So that shows that this guy is our universal cone, or our like limiting cone over this compatible family. So the other question I asked was kind of a little bit easier. So I wanted to know, why do I have these two assumptions in this problem? So the problem was as follows. If I've got my ambient category is the post set of real numbers with less than equal to sign as our order. And I consider a diagram in here to be a non-empty bounded above subset. So non-empty is because I want to talk about a diagram. And so if I don't have anything to point at, then I can't really do any kind of interesting limits. So that's why I want non-empty. So there's something to talk about in there. Bounded above means back. So let's talk about what bounded above means in the general sense. Um, like what the definition is, and then we'll look at it how it relates to this problem. So bounded above means that there exists some upper bound of the entire set. So there exists some number, say lambda in R, such that for all x in E, we have x is less than or equal to lambda. So that means that there exists an upper bound. That's the usual definition. The way we use it here is that when I include E, less than equal to as a subcategory of this post-it category, it means that I have kind of non-empty sets of morphisms. That means for all x in E, maybe I should check this. There exists a real number such that for all x in E, from x to lambda is not empty. So we recall with this poset category notation, the morphisms from x to y are either a singleton set or they're empty. So it either consists of a single morphism from x to y if x is less than or equal to y, or it's empty otherwise. So the morphisms are just keeping track of the order relation between the elements. In this case, the data of a single upper bound is the same thing as the data of a cocone over E. So this is a cocone over E. Being a universal cocone is the same thing as being the colimit of this inclusion diagram. But you can't have like a universal cone if you have no, or universal cocone if you have no cocones to begin with. So saying that E is bounded above is the same thing as saying that there's some diagram that we can limit over. That's all. Yeah, so the punchline of that one is that the limit over all such things, this inclusion, it's the same thing, or the colimit rather, is the same thing as the supremum of E. So there weren't any other questions I think I had really asked of everybody. Um, so these are all the ones I was kind of planning on doing. Um, so I can stop the recording here and then um, see you guys next time. I can give out more problems next time so there's more to talk about. Um, but yeah. Do you have any questions? Sole attendee? No. Okay. All right. See you guys next time.